Shown is the atomic symbol model for ethanolamine, one of the moieties used as a phospholipid head. Note, this is a polar molecule because it has positive and negative charges. The amine has a full ionic positive charge. The hydroxyl has partial positive and negative charges. The CH2 groups also have partial positive charges, although these are much lower than either the hydroxyls or amines. Now the space-filling model of ethanolamine is displayed. Here is our ethanolamine in the water lattice. The polar compound interacts with the lattice. It does not disrupt it as a hydrocarbon would. Water's negative oxygens are attracted by the positive charges of the polar compound, while water's positive hydrogens bind negative charges. This is why polar compounds are water-soluble, hydrophilic. They integrate with the water lattice. Dimming the water molecules makes it easier to observe their electrostatic interactions with the polar compound. Water's charges interact with the opposite charges of the compound. The assemblage of water molecules around a polar compound is known as a hydration shell. Phosphatidylglycerol has been bound to ethanolamine, producing the phospholipid phosphatidylethanolamine. The non-polar hydrocarbon tails disrupt the lattice, producing an unfavorable conformation. This is why they align side by side. This arrangement minimizes interactions between the water and the tails. The polar head interacts with and integrates into the lattice. To display the 5 classes, 4 additional phospholipids have been introduced. The 5 classes are, from top to bottom, phosphatidylserine, phosphatidylcholine, phosphatidylethanolamine, phosphatidylnositol, and phosphatidylglycerol. Each class is defined by a different head: serine, choline, ethanolamine, inositol, or glycerol. Different members within a class are defined by different hydrocarbon tails. This image displays the basic structure of a biomembrane. To minimize exposure to the water matrix, the hydrophobic tails align in parallel, held together by hydrophobic van der Waals forces. The hydrophilic heads align on the surface of the membrane, where they integrate into the lattice.